Chapter 10, Hypothesis Testing. Section 10.1, Hypotheses. A hypothesis is a falsifiable claim that requires verification, typically from experimental or observational data, and that allows for predictions about future observations. Let's unpack that definition. Falsifiable is perhaps the most important word in that definition and is the basis for progress in science. Falsifiability means that a claim can be disproven, which allows scientists to test and refine ideas of the natural world. It may seem odd to focus on disproving ideas instead of proving them, but in fact, scientific claims cannot be proven beyond a reasonable doubt. They can be disproven or fail to be disproven. There are philosophical and statistical reasons for this, which I'll explain later in the chapter. Why is it important that a claim be falsifiable? I can claim that fantastical fairies are friendly on Fridays, but there's no way to verify that claim, which means that that claim cannot be used to help us understand the universe and anything in it. To be clear, there is nothing inherently wrong with non-falsifiable claims. They can be fun to think about and can inspire the imagination and add value to life. Footnote. For example, the claim, "Love makes the world go round," is not falsifiable, but has inspired countless poems, songs, books, movies, and wars. Back to the text. Even in the realm of science, non-falsifiable claims can help kickstart brainstorming, interpretations, and experiment design. But when it comes to specifying hypotheses and using statistics to evaluate those hypotheses, only falsifiable claims are relevant. Section 10.1.1, How to Specify a Hypothesis. Hypotheses do not magically materialize out of thin air. Instead, hypotheses are stepping stones along the path of scientific progress. Science is a never-ending progress of creating new hypotheses by observing data or improving existing hypotheses. Many hypotheses start with a research question, which is then refined into a hypothesis. A research question is a question about the relation between two or more variables. For example, we might ask, does coffee help university students? That is not a hypothesis. It is a question about whether one variable, coffee, is related to another variable, something about students, although the question doesn't specify what coffee helps. Research questions can be translated into hypotheses by making a statement that forms a direct link between the variables. For example, we can hypothesize that 1 to 2 cups of caffeinated coffee per day increases exam scores in first-year university students. Notice that this hypothesis is specific and concrete. It specifies the amount of coffee, 1 to 2 cups, the relevant population, first-year university students, a concrete measurable outcome, exam scores, and the direction of the effect, increased scores. This is merely one hypothesis. Many hypotheses can come from a single research question. We might also hypothesize that coffee improves students' social lives, that it impairs sleep quality when consumed after 4 p.m., that it creates on-campus jobs for students working in cafes, and so on. Back to the definition at the outset of this section. Footnote. As a reminder, a hypothesis is a falsifiable claim that requires verification, typically from experimental or observational data, and that allows for predictions about future observations. Back to the text. All hypotheses must be verifiable, but not all hypotheses need to be verified with experimental or observational data. Some hypotheses can be verified using mathematical arguments, simulated data, or logical reasoning, but these kinds of hypotheses are not relevant for statistics. In statistics, and certainly in the statistics covered in this book, we are interested in hypotheses that can be evaluated with data. The final point about the definition of hypotheses is that they allow for predictions about the future. This means that the hypothesis will generalize to a wider population that includes data collected in the future. For example, I can hypothesize that the global stock market last week fluctuated with my mood. And with only 5 data points, this hypothesis might seem valid, but that hypothesis is not going to be useful for predicting the stock market in the future. Section 10.1.2. Why do we need hypotheses? You don't always need hypotheses to do science or to make discoveries about the world. In fact, many areas of science begin with simple observation. Ecological research is an example. Let's say you travel to a remote island and observe butterflies with purple wings. That observation increased our understanding of the world without a hypothesis. As scientific knowledge progresses, observation-based studies develop into hypothesis-driven studies. In this example, subsequent research on the island might be driven by the hypothesis that purple butterflies attract more mates than non-purple butterflies. There are several advantages of hypothesis-driven research. Advantage 1, hypotheses improve experiment design, critical thinking, and data analyses. Advantage 2, hypotheses transform loose ideas into concrete and specific claims. Advantage 3, hypotheses help develop new and better theories and to dissolve bad theories. Advantage 4, hypotheses enable rigorous and quantitative evaluation. Advantage 5, hypotheses lead to an understanding of underlying mechanisms. In my humble opinion, point number 5 is the most important. Discovering the state of the world by observing it is great, but hypotheses help us understand why the world is the way it is, which in turn helps us change the world. Section 10.1.3, Strong and Weak Hypotheses. Not all hypotheses are equal. We can distinguish strong from weak hypotheses. As you can imagine, strong hypotheses are preferred when possible. Any hypothesis should be clear, specific, falsifiable, based on prior data or theory, amenable to statistical evaluation, a statement, not a question, a prediction about a direction of the effect, relevant for unobserved data or phenomenon, and relevant for understanding nature. But a strong hypothesis has more of those qualities than a weak hypothesis. Here are a few examples. Medical research is important to cure diseases. This is not an hypothesis. It is a statement that many people agree with, but it is not a scientific hypothesis. Will medication X help patients? This is a research question, not a hypothesis. The medication has an effect. This is a weak hypothesis. It is consistent with the definition of an hypothesis, but it is not specific about the nature, direction, or duration of the effect. Medication X reduces symptoms of disease Y in a dose-dependent fashion. This is a stronger hypothesis than the previous one because it is concrete and specific. Notice the difference between the weak and strong hypotheses. The weak hypothesis predicts some kind of effect, but provides no specifics as to the nature or direction of the effect. Why even bother with weak hypotheses? Shouldn't we just agree that weak hypotheses are pointless and are banned from scientific discourse? In some cases, weak hypotheses come from lazy researchers, and this is something to avoid. But we should not disparage all weak hypotheses. Weak hypotheses can indicate that too little is known to generate strong hypotheses. For example, imagine that a government introduces a new tax policy. Independent researchers might not have enough information to make a strong hypothesis about the impact of the tax policy, And so instead, we'll hypothesize that the new policy will influence consumer spending behavior. After a few years of collecting data and testing weak hypotheses, researchers will be able to generate stronger hypotheses. New scientific disciplines progress from observations to weak hypotheses to strong hypotheses. So, try to make your hypotheses as strong as possible while acknowledging that having a weak hypothesis is not necessarily a weakness in you or in your research. Pop quiz. Determine whether each statement below is a weak or strong hypothesis or not an hypothesis. I will give my answers after reading each item. Statement 1. There are other universes with different physical laws. Answer. Fascinating idea, but not an hypothesis because we cannot falsify it. Statement 2. Wearing purple underwear improves mood. Answer. Strong. Statement 3. Plants grow differently in sugar water. Answer. Weak. Statement 4. Mike X Cohen's books are awesome. Answer. Not an hypothesis. It is an unprovable opinion that I hope at least a few people have. Statement 5. Washing hands for 20 seconds reduces the spread of infectious diseases. Answer. Strong. Statement 6. An apple a day keeps the doctor away. Answer. Could be a strong hypothesis if keeps the doctor away were rephrased, for example, as leads to fewer hospital visits. Statement 7. Are people more creative after watching stand-up comedy? Answer. A research question, but could be formulated into an hypothesis. I hope you are starting to feel more comfortable with hypotheses, and I'm sure you're getting increasingly curious about how to quantitatively test hypotheses. Some mechanisms of hypothesis testing are general to all hypotheses, while many other mechanisms are specific to the nature of the hypothesis and the characteristics of the data. In the rest of this chapter, you will learn about general aspects of hypothesis testing. The specifics of hypothesis testing are organized into chapters in the rest of this book. Section 10.2, IVs, DVs, models, and other stats lingo. You've already seen in this book that there are many terms to know in statistics. And to make matters worse, some terms are confusing, overloaded, or inconsistently used in different scientific communities. There isn't much I can do about that except try to be clear and consistent in this book, although I'm sure I fail at that occasionally. Below are some important terms related to hypotheses and hypothesis testing. You will see these terms throughout the rest of this book. Dependent variables, often abbreviated DVs. A dependent variable, also called an outcome variable, is a feature of the data that you try to explain. Examples of DVs include disease outcome in a medical study, weight loss after a diet regimen in a health study, number of clicks in an online marketing study, and income in an economics study. It is common for a study to have only one DV, but studies may have multiple DVs. For example, a study on job satisfaction might have 3 DVs: self-reported satisfaction, supervisor-reported performance, and employee-attributed revenue. Independent variables, often abbreviated IVs. An independent variable is a variable that you use to explain changes in the DV. Some IVs are experimentally manipulated or controlled, for example, the medication dose in a medical study, while others are measured but not manipulated. For example, self-reported time spent watching YouTube videos. IVs are also sometimes called explanatory variables, predictor variables, or regressors. Most studies have more IVs than DVs. The distinction between IVs and DVs is important. Statisticians use IVs to explain the DV. Figure 10.1 shows examples of independent variables and dependent variables in different types of studies. This paragraph references Figure 10.1, which shows a table with examples of DVs and IVs in different studies. Some variables are numerical, while others are categorical. This has implications for the appropriate statistical analyses, as you will learn later in this book. The table has 4 rows and 3 columns. The first column is labeled research, the second column is labeled DV, and the third column is labeled IVs. So we have in the first row, research type is cancer, the DV is mortality, so alive or dead, and the IVs are age, exercise, encoded as minutes per week, and cancer type. Second row is weight loss, and then we have the DV is weight change, and the IVs are diet type, exercise, and sleep, encoded as hours per week. Third row is e-commerce research, the DV is profit, and the IVs are overtime hours, Twitter budget, Google ad budget, and Facebook ad budget. The final row is psychology research, the DV is self-reported mood, and the IVs are hours per day spent on social media and gender. So these are just some examples of DVs and IVs in different types of research. Back to the text. IVs and DVs are not fixed in their roles. Imagine a data set with information on factors that explain subjective wine quality, including variables such as sugar content, amount of alcohol, age, region of origin, and subjective quality ratings. We could use this data set to predict wine quality ratings, and we could use the same data to predict the region of origin. In other words, a variable can be an IV in one analysis and a DV in another analysis. But within one analysis, there is one DV to predict and one or more IVs to make those predictions. Residuals. The IVs rarely explain the DV in its entirety. For example, imagine a data set comprising data on weight, age, height, and minutes of moderate weekly exercise in 500 adults, and imagine that our goal is to explain variance in weight, that's the DV, using the other variables as IVs. Obviously, we won't be able to predict 100% of the individual variability in weight based on those factors. The difference between what the IVs explain and the observed weight are the residuals. In other words, the residual is the difference between the observed DV and the predicted value of the DV. Residuals are also called errors, deviations, or innovations. Model. There are many kinds of models in statistics, excluding the attractive people who make money by associating their beauty with products or services in magazines and viral TikTok videos. Generally speaking, a model is a framework for interpreting data. Models vary in their depth, specificity, explanatory ability, and mathematical detail. In this book, when I use the term model, I am referring to a mathematical formula that links the IVs to the DV in a form that looks something like the following. Y equals beta sub 1 x sub 1 plus beta sub 2 x sub 2 plus beta sub 3 x sub 3 plus epsilon. Y is the DV that we are trying to explain using the 3 IVs, x sub 1, x sub 2, and x sub 3. The beta values encode how much each IV contributes to explaining the DV, and epsilon represents the residual, the variability in the DV that the IVs cannot account for. Here's an example. I have an hypothesis that the height of adult humans depends on their mother's height, their father's height, and their childhood nutrition, quantified as a score ranging from 0 to 10. Height is the DV, that's variable y, and the parents' heights and childhood nutrition are the IVs, x sub 1, x sub 2, and x sub 3. I assume that these IVs are important, but I do not know how important they are. A regression analysis would compute the scaling factor is beta. Now, needless to say, someone's height is determined by more than just these three factors, and so the residual variance in height is captured by epsilon. You will learn the specifics of how to transform an hypothesis into a model, how to fit models to data, and how to determine the statistical significance of models in subsequent chapters. For now, I want you to understand that a hypothesis is translated into a mathematical equation that links the IVs to the DV, and we call that equation a model. Test statistic. A test statistic is a descriptive statistic of a dataset that is associated with an hypothesis. Most inferential statistics involve determining the probability that the test statistic could have been observed by chance due to noise or sampling variability, instead of being a real effect in the population. There are many test statistics. Examples include correlation coefficient, t-value, f-value, and chi-square value. The generic term, test statistic, is used when discussing concepts and methods that apply to all test statistics. Null and alternative hypotheses. Inferential statistics involve evaluating the fit of a model to data. In many cases, the important statistical result, such as a p-value, reflects a comparison of two models, which are derived from two hypotheses. The two hypotheses are termed null and alternative. The null hypothesis states that there is nothing interesting happening, no relation between the DV and the IVs. The mathematical equation associated with the H0 or H0 sets some or all of the beta scaling parameters to 0. You can think of the null hypothesis as the assumption that there's no relationship amongst the variables of interest. The term null hypothesis, when written out, is often abbreviated as H sub 0 or H0. It's generally pronounced H0. The alternative hypothesis is often abbreviated as H sub A or HA. This is the hypothesis that you specify in your research. It is the alternative to the null hypothesis. Now, I think a better term would be the effect hypothesis, because the hypothesis specifies that there is an effect, not that there is an alternative, but this is the term that everyone uses. Sometimes you will see H sub 1, H sub 2, and so on when there are multiple alternative hypotheses. Here's an example of an alternative and null hypothesis. H sub A, people will buy more widgets after seeing advertisement X compared to advertisement Y. H0, the type of advertisement has no effect on widget purchases. Section 10.3. Can you prove an hypothesis? It may seem obvious that the purpose of generating an hypothesis is to prove it, and that the purpose of statistics is to quantify whether the hypothesis is true, as in proven, or false, as in disproven. Well, unfortunately, it's not that simple. Well, disproving an hypothesis can be simple. You need only a single observation that is inconsistent with the hypothesis to disprove that hypothesis. For example, if I have an hypothesis that all humans have purple skin, we would need to find only one human without purple skin to disprove this hypothesis. Other hypotheses are more difficult to disprove. The hypothesis, no human can be taller than 272 centimeters, can, in principle, be disproven by observing a human taller than 272 centimeters. But in practice, that tall human may not be alive right now or may not have been measured. Many hypotheses in fields related to biology cannot be disproven in practice. Footnote. In mathematics, hypotheses can be proven through a sequence of equations and axioms, but that's actually a different type of hypothesis from what empirical scientists deal with. Back to the text. This is due to a variety of factors, including having underspecified or weak predictions, individual differences, sampling variability, measurement noise, and limited sample size. For example, I have an hypothesis that showering with socks on my feet increases my book writing productivity by 7 words a day on average. That is a perfectly valid, if somewhat strange, scientific hypothesis, but the predicted effect size is so small, and there are so many other factors that contribute to my book writing regimen that definitively disproving that hypothesis is practically infeasible. So the reality is that many hypotheses, especially hypotheses that involve complex organisms like humans, are not actually disproven. Such hypotheses can, however, be supported by data or inconsistent with data. But that's not the same thing as being proven or disproven. Perhaps you find this situation unacceptable. Why bother with hypotheses if they cannot be definitively disproven? This opposition has merit. Scientific progress would arguably be faster and more efficient if all hypotheses could be undeniably accepted or disproven. But the reality is that our understanding of nature is so meager, and our desire to understand it so great, that limiting ourselves to definitively disprovable hypotheses would bring scientific progress to a standstill. Instead, we accept and embrace imperfections as part of the path to progress. Even when the data are consistent with an hypothesis, we never take the hypothesis as true. Instead, we agree to tentatively hold on to that hypothesis until we develop a better one. This may seem like a subtle linguistic twist, but I cannot understate how important this is. Never believe a hypothesis or consider an hypothesis to be true. That impedes scientific progress, and it risks turning you into a recalcitrant and closed-minded researcher. Instead, you consider an hypothesis to be good enough to work with until you or someone else develops a better, stronger, and more accurate hypothesis. Why can't we accept hypotheses as being true? Remember that hypotheses are translated into mathematical equations. When you collect data and find that the alternative model fits the data better than the null model, that doesn't imply that HA is proven, nor does it imply that HA is the best possible model. There could be better and more accurate models that you have not considered. The only valid conclusion is that the alternative hypothesis is, with some probability, better than the null hypothesis. This is an important statistical and philosophical concept. Just because a model fits some data does not mean that that model is correct. Here's a simple example. Let's say I have two variables whose numerical values are x1 equals 1 and x2 equals 2, and the outcome variable is y equals 3. What is a model that relates the IVs to the DV? Well, I'm sure you guessed x1 plus x2. That's a good model, but is it the only model? Of course not. It could be y equals minus 5 times x1 plus 3 times x2. Or perhaps y equals x1 cubed plus the square root of x2 squared, or an infinite number of other possibilities. We do, however, know that we can rule out other models like y equals x1 minus x2. That model is inconsistent with the data. So, given the infinity of possible models, how can we choose one? In practice, we choose a model by imposing constraints on that model based on assumptions. Some of those assumptions come from theories, some of those assumptions come from intuition, and some of those assumptions come from the convenience of simplicity. For example, the model with the square root term is more complicated, and so we would avoid it unless the complications turn out to be necessary to explain other data. Footnote. The assumption that simplicity is better than complexity is known as Occam's razor, and is an example of how the human subjective perception of aesthetics guides our investigations into nature. Whether this is a valid scientific principle is a matter of debate. Back to the text. The point is that we can never know if we have the correct model or the best model. We can, however, know which model is best among the models we are comparing, which is usually HA versus H0. That is why you cannot prove an hypothesis. You can either disprove it, or you can show that the data are more consistent with HA compared to H0. Section 10.4, Sample distributions under the null hypothesis and alternative hypothesis. You know from the previous chapter that repeated samples of a population will have different means, and that the distribution of those sample means will approach a Gaussian shape with the dispersion given by the SEM, which itself is the sample standard deviation scaled by the square root of the sample size. This variability in sample means is the basis for providing statistical support for or against an hypothesis. Let's start with an hypothesis and an imaginary experiment. I have an hypothesis that caffeine improves mood, a reasonable hypothesis considering that caffeine activates dopamine and adenosine receptors. Here are the formal statements of my hypotheses. HA. 1 cup of caffeinated coffee increases self-reported emotional state 1 hour after consumption. H0. 1 cup of caffeinated coffee has no impact on self-reported emotional state 1 hour after consumption. To test this hypothesis, we conduct an experiment in which 200 research participants are given 1 cup of coffee that is either caffeinated or decaffeinated. So 100 participants in each group, double-blinded so that neither the participants nor the researchers know who gets what coffee. They self-report their emotional state before the coffee and 1 hour after the coffee. Now, emotional state is a complex, multifaceted construct, but for simplicity, let's say it's rated on a 10-point scale from 1, indicating worst mood ever, to 10, indicating best mood ever. The DV is the change in mood from pre to post coffee. We can translate the experimental hypothesis into a mathematical model in equation 10.1, which reads delta equals beta C plus epsilon, where delta is the change in self-reported emotional state, post-coffee minus pre-coffee. C is the coffee condition, labeled as 0 for decaf and 1 for caffeine. Beta includes the impact of caffeinated coffee on the change in mood, and epsilon captures the change in moods that are caused by anything other than the coffee caffeination. Now let's translate the competing hypotheses into mathematical expressions. In the equations below, I use delta bar to indicate the change in self-reported emotional state averaged over the sample. The subscript C and D indicate caffeinated and decaffeinated groups respectively. So HA is delta sub C bar is greater than delta sub D bar. H0 is delta sub C bar equals delta sub D bar. A few things to note about these equations. Note 1. It is important to state the hypotheses in words that are easily understood, but translating those words into math increases precision and compactness. Note 2. For this experiment, we'd need a control group, decaf coffee, because it is possible that mood increases 1 hour after drinking any hot beverage, regardless of its psychoactive properties. Without this control group, the null hypothesis of delta C equals 0 is called a strawman hypothesis. Note 3. The hypothesis gives a specific direction for the effect. I could have written caffeine changes mood and translated that into delta sub C bar not equal to delta sub D bar. This is the difference between a one-tailed and a two-tailed hypothesis and corresponding statistical tests, which I will discuss in more detail later in this chapter and in subsequent chapters. Note 4. The average change refers to the average over the sample of 100 participants in each group. It is not necessary for each participant to show an increase in emotional state. The hypothesis will still be supported as long as the average mood increases, even if mood decreases for some people. Note 5. It is sometimes useful for conceptual or mathematical reasons to set the equation to 0. So the two hypotheses could be rewritten as delta sub C bar minus delta sub D bar is greater than 0, and delta sub C bar minus delta D bar equals 0. Final note, related to the previous point, in some analyses like regression, the hypotheses are more directly linked to the model. For example, referring back to equation 10.1, we can write H0 is beta equals 0 and H0 is beta is greater than 0. To simplify the discussion below, I will set capital delta equals delta C bar minus delta D bar. This means that our hypothesis is capital delta is greater than 0, and the null hypothesis is capital delta equals 0. Once we have the data, how do we test our hypothesis? Let's imagine that the true state of the world is H0. That is, we know with 100% certainty that caffeine has no impact whatsoever on emotional state. You may be saddened to read this, but don't worry. It's just a thought experiment. What is the expected value of capital delta? I'm sure you guessed it. We expect capital delta equals 0, but that's the theoretical expected value. What do you expect to happen in an empirical sample of n equals 200? Due to sampling variability, individual differences, and myriad other factors that impact mood fluctuation, capital delta probably won't be exactly 0. And what if we repeat the experiment again with a new sample of n equals 200, and another sample, and another sample? You see where this is going. We would get a distribution of capital delta values. The law of large numbers tells us that the average of these sample means will converge to 0, and it converges to 0 because we assume that the true state of the world is capital delta equals 0. And the central limit theorem tells us that the distribution of those means will converge to a Gaussian. Figure 10.2 shows an imaginary distribution of capital delta values from repeating the experiment 1,000 times in a universe where coffee has no impact on emotional state. We see a histogram where the x-axis is the difference value, or capital delta, the y-axis is count, and the distribution looks roughly Gaussian, centered on a capital delta value of 0. Back to the text. That distribution of H0 capital delta values is from an alternative universe where we know with absolute certainty that coffee has no impact on emotional state. Now, back in our universe where we don't know the true effect, we have our empirical capital delta. Let's imagine two possible outcomes. Outcome A is capital delta equals 0.1, and outcome B is capital delta equals 0.7. Numerically, both outcomes are greater than 0 and thus consistent with our hypothesis. But when plotted on top of the H0 distribution, outcome B looks more compelling. This paragraph refers to figure 10.3, which illustrates a theoretical distribution of capital delta values, assuming that the null hypothesis is true, that is, capital delta equals 0 with sampling variability. The two vertical dashed lines indicate possible capital delta outcomes in an experiment where our goal is to determine whether capital delta is greater than 0. We see in this figure a histogram that is the same as the histogram that I described for figure 2, 10.2. And then we see two vertical dashed lines. One is very close to the center. It's just a little bit above 0, so it's well within the mass of the null hypothesis distribution. That corresponds to capital delta equals 0.1, which is option A, outcome A. And then we see much further away towards the right tail of the distribution is a vertical dotted line corresponding to option B, which is capital delta equals 0.7. Back to the text. Why is outcome A less compelling? It's because it fits neatly into the H0 distribution. In fact, the probability of observing capital delta equals 0.1, given that the null hypothesis is true, seems rather high. Therefore, outcome A does not provide enough evidence to reject the null hypothesis in favor of the alternative hypothesis. We would conclude that caffeine does not increase emotional state in this experiment. What about outcome B? The value of capital delta is technically still inside the null hypothesis distribution. In other words, even if the null hypothesis were true, we could expect to observe values as large as, or even larger than, the empirical capital delta. But such a large value is unlikely compared to the value for outcome A. So we can say that outcome B is so unlikely, though not impossible, to be observed if the null hypothesis were true, that we decide to reject H0 in favor of the alternative hypothesis. A meta comment. Would you consider my alternative hypothesis to be weak or strong? We can imagine a progression of hypotheses from caffeine impacts thoughts and feelings, to caffeine improves emotional state, to caffeine boosts positive affect with a half-life of 4 hours, to caffeine induces positively valenced emotions by stimulating A2A receptors in the ventral striatum, and so on. This is an example of how science progresses by building stronger hypotheses on top of weaker ones. I hope this and the previous sections instilled some intuition about how the law of large numbers, the central limit theorem, and the null and alternative hypotheses come together to provide evidence against the null hypothesis in favor of the alternative hypothesis. But my interpretation of the strength of the evidence was subjective and based solely on visual inspection of the H0 distribution. We need to attach a numerical value to that subjective evaluation. In other words, we need to obtain an exact probability that the descriptive statistic capital delta in our empirical data set could have been obtained if the null hypothesis were true. That probability value is called a p-value, and it is the single most important numerical quantity in applied statistics. I'm sure you are very excited to learn about p-values, but there is one more thing I'd like to discuss about H0 distributions before formally defining p-values. Please keep listening. Section 10.5, where do H0 distributions come from? How do you create a null hypothesis distribution to compare the observed findings against? You cannot create an alternate universe where you know with certainty that H0 is true and then collect more data points than grains of sand on all the beaches in the world. And yet, we need the H0 distribution to evaluate the probability that the observed test statistic is due to chance. H0 distributions come from one of two sources. Source 1, analytical H0 distributions. This is, by far, the most common source of H0 distributions. With the analytical approach, the null hypothesis distribution comes from a mathematical formula. The exact mathematical formula and how you set its parameters depends on the type of test you are performing. For example, an F-test or a T-test or a Z-test. And on some details about the experiment, such as the sample size and the number of conditions. You will learn the details of how to choose the formulas later in this book. The important point for now is that the H0 distribution comes from a mathematical formula and that it is obtained without any data. Source 2, empirical null hypothesis distribution. This is the approach taken in computational statistics, such as permutation testing, which you'll learn about in Chapter 16. The idea of creating an empirical null hypothesis distribution is to randomize your data to create an artificial dataset, also called a shuffled, permuted, or surrogate dataset, that could arise under the null hypothesis. It is essentially a way to create fake data that have the same characteristics as your real data, but where you know that H0 is true. An empirical H0 distribution requires already having data. It cannot be created without data. Figure 10.4 shows examples of two sources of null hypothesis test statistic distributions. The analytical null hypothesis distribution is a smooth line because it is generated from a mathematical formula and can be evaluated at any desired resolution. The empirical null hypothesis distribution is a histogram because it is generated from data that have been randomly repeated. Most statistics, and therefore most of this book, will deal with analytical null hypothesis distributions. In Chapter 16, I will introduce empirical null hypothesis distributions, their advantages and limitations, and when to use them. This paragraph refers to Figure 10.4, which illustrates an analytical null hypothesis distribution in panel A, and an empirical null hypothesis distribution in panel B. Panel A, the analytical null hypothesis distribution, is a curved line. It just looks like a pure Gaussian. Panel B is a histogram that also looks roughly like a Gaussian, but it is not a perfect Gaussian because it is sampled from random data. Section 10.6, P-values, definition, and misinterpretations. The p-value is the probability of obtaining the observed test statistic if the null hypothesis were true. The smaller the p-value, the less likely it is that the null hypothesis is the true state of the world, and your results were due to chance, noise, sampling variability, unexplained factors, and so on. It is that simple. A p-value is the probability of obtaining a result given that the null hypothesis is true. Slightly more accurately worded, the p-value is the probability of obtaining a test statistic as extreme as, or more extreme than, the observed test statistic under the assumption that the null hypothesis is true. Reiterating an important concept, a small p-value does not prove that the alternative hypothesis is true. We can only compute the probability that the test statistic associated with the alternative hypothesis could have been observed, given that there is no true effect. A small p-value means that the data are more consistent with the model specified by HA compared to the model specified by H0, but that doesn't mean that HA is true. Despite their definitional simplicity, p-values are nuanced and often misinterpreted. Your understanding of p-values will continue to increase throughout the rest of this book. Section 10.6.1, P-values and statistical significance. The term statistical significance is used to indicate that we reject the null hypothesis in favor of the alternative hypothesis. The p-value is the key quantity that allows us to label a finding as statistically significant. P-values are continuous and range from 0 to 1, but for interpretation, p-values are binarized into a range for statistical significance and a range for statistical non-significance. A typical threshold is p equals 0.05, although other thresholds are sometimes used like p equals 0.01 or p equals 0.001. Any test statistic with a p-value smaller than the threshold is deemed statistically significant. The p-value threshold to determine significance is indicated using the Greek letter alpha. Thus, a p-value threshold of 0.05 for statistical significance can be expressed as alpha equals 0.05 or alpha equals 5%. The concept of carving the H0 test statistic distribution into a significant and non-significant regions is illustrated in figure 10.5. Panel A shows a distribution of test statistic values, assuming that H0 is true, and panel B shows the probability of obtaining each test statistic, which is the p-value. Any test statistic with an associated p-value less than 0.05 is considered statistically significant, as indicated by the shaded regions. This figure illustrates a two-tailed test, which I'll discuss in more depth in the next section. This paragraph refers to figure 10.5. Figure 10.5 shows three panels organized in one column. Panel A on top is a Gaussian distribution, and the title of this panel is Test Statistic Distribution if H0 were true. So here we see on the y-axis the probability given the null hypothesis. On the x-axis we have the test statistic value, which in this case is a z-score. So we see a Gaussian distribution, and there is a vertical dotted line at somewhere close to 2 and a little bit over -2. And the region in between the x-axis and the Gaussian curve to the right of the dotted line at around 2 and to the left of the dotted line at around -2, these little regions are shaded in gray and indicated as being significant. The white region in the middle between -2 and +2 is labeled non-significant. In panel B, we have the p-values for the test statistic values. This is not a Gaussian distribution. It starts off close to 0 and it goes up to 1, and then it does go back down to 0, but there's a point in the middle instead of a round hump. Here we have the vertical dotted lines as in panel A, also going through panel B, and also the shaded regions on the two tails indicated here as statistical significance regions. There is a horizontal dashed gray line corresponding to a p-value of 0.05, indicating that when we have a p-value of less than 0.05, then that corresponds to test statistic values that are far away from 0. Panel C shows the same thing as panel B, but the y-axis scale is logarithmic instead of linear as in panel B. This simply helps us visualize the tails of the distribution. Back to the text. The shaded areas in the p-value function in panel B are so tiny that I decided to replot the function using logarithmic scaling in panel C. The difference between panel C and B shows that logarithmic visualization is often useful when showing functions in areas that asymptotically approach 0. The shape of the p-value function in figure 10.5b may look strange, but it comes directly from the CDF of the normal distribution that is inverted for z is greater than 0. This is a concept that was introduced in exercise 8.10. In other words, the p-value corresponds to the CDF for z less than 0 and 1 minus the CDF for z greater than 0. This is because the probability of extreme values decreases as the test statistic values increase on either side of the H0 distribution. Sometimes people add a third category of p-values in between 0.05 and 0.1. Such findings are called marginally significant. Usually this term is used when someone wants the finding to be significant, but it is above the typical 0.05 threshold. Section 10.6.2, P-values and distribution tails. You learned in Chapter 3 that distributions have two tails. Distribution tails are relevant for hypothesis testing because hypotheses are not always specified in one direction. In particular, there are three possibilities for specifying an hypothesis, depending on whether you predict a positive effect, a negative effect, or any effect other than 0. Translated into math, we have one-tailed effects as either capital delta less than 0 or capital delta greater than 0. And then we have a two-tailed test, which is capital delta not equal to 0. Two-tailed tests map onto a weak hypothesis, no predicted direction of the effect, while one-tailed tests map onto a strong hypothesis. Figure 10.6 illustrates the difference between one-tailed and two-tailed hypothesis testing. The H0 distribution is the same for both tests. The difference is whether we consider test statistic values only from one side or from both sides. This paragraph references figure 10.6, which illustrates one versus two-tailed tests. We see two Gaussian curves on top and on bottom. The top panel shows a one-tailed test, and the bottom shows a two-tailed test. We see the Gaussian curve, and then to the right in panel A is a vertical dashed line corresponding to the significance threshold, and the area above that line to the right of that line is demarcated as 5%. Then in panel B, we have the Gaussian curve is the same, but now there are two significance threshold vertical dashed lines on the right tail of the distribution and on the left tail of the distribution. The right tail line is actually further to the right compared to the vertical dash significance threshold line above it in panel A, and the shaded areas on the left tail and the right tail are each demarcated as 2.5%. So the total area for rejecting H0 is the same. The question is whether that area comes from one side or is split between both sides. Back to the text. You might be surprised to learn that statistical significance is usually based on two-tailed tests, even when the hypothesis specifies a direction. You might think that we should always use one-tailed tests for hypotheses that predict the direction of the effect. Although this is sometimes acceptable, the culture in statistics has evolved to use two-tailed tests nearly all the time, even if the hypothesis specifies only one tail. In part, this is to allow for unexpected findings. After all, science would be dreadfully boring if we always knew the outcome. And in part, it makes the hypothesis a bit more difficult to label as significant. In fact, if you try to publish a one-tailed result, your audience might become suspicious that you are trying to p-hack that result. The conclusion is that you should use two-tailed tests even when your hypothesis predicts one tail. But one-tailed tests are also used. For example, the F-test in ANOVAs and regressions are one-tailed because the H0 distribution is positive valued. Another example is with data that have a power law distribution, which has only one tail. Section 10.6.3, where do p-values come from? Because a p-value is defined as a probability of a particular value given the null hypothesis distribution, and because null hypothesis distributions come from one of two methods, analytical or empirical, p-values also come from one of two methods. Analytical p-values. The analytical p-value is computed from a formula that transforms a test statistic into a probability of observing a test statistic at least that large in a theoretical null hypothesis distribution. As an example, let's focus on z-scores and see how to map those onto p-values. You know that z-scores reflect the normal distribution with 0 in the middle and the numbers encoding the standard deviation distance to the center. So what is the probability of z greater than 1? We can answer this question by computing the area to the right of z equals 1 in the PDF corresponding to the normal distribution. In this case, the probability of z greater than 1 is p equal to 0.158. This paragraph references figure 10.7, which shows a Gaussian curve with a vertical dashed line at z equals 1, and the area of the under the curve above that line, or to the right of that vertical dashed line, is shaded in and demarcated as 15.87%. The figure caption reads, about 16% of the area of a normal probability distribution is greater than one standard deviation above the mean. Back to the text. A note about implementation. The figure shows a PDF, but in practice, p-values are computed from the CDF. And because a CDF is the area to the left of the specified value, the area to the right of that value is 1 minus the CDF value. You can see this implemented in the online code that produces figure 10.7, and you'll gain more familiarity with this in the exercises here and in the next chapter. Empirical p-values. If you are using permutation-based statistics to create an empirical null hypothesis distribution, the p-value is computed as the normalized distance of the test statistic to the center of that H0 distribution, or as the number of H0 values more extreme than your observed test statistic. I'll explain that in a lot more detail in chapter 16. Before then, we will exclusively use analytical p-values. Importantly, the interpretation of a p-value is always the same, regardless of how it is computed. Precision of p-values. P-values can be computed to an arbitrary precision, just like how the square root of 2 can be computed to an arbitrary precision. In practice, p-values are truncated or approximated. For example, a p-value of exactly p equals 0.02, that is p equals 0.0200000000, is galactically unlikely in real data, but in the interest of convenience and brevity, people will write p less than 0.05, or p less than 0.02, or just p equals 0.02. When the p-values get really small, they are indicated with scientific notation, for example, p less than 10 to the minus 7. Section 10.6.4, P-Z combinations to memorize. Math teachers love to say things like, don't memorize, understand. That's an easy claim to make when you've been teaching the same material for years or decades. The truth is that many concepts and formulas in applied math just need to be memorized. Because z-values, that is, standard deviation units in a normal distribution, are so important in statistics, and because probability values are directly mapped onto z-values, there are some p-z combinations that I think you should commit to memory. These pairs will help you build intuition for data cleaning, analysis, and interpretation, and they will make you look like an impressively knowledgeable statistician. This paragraph references figure 10.8, which shows a Gaussian distribution or a bell curve distribution, a normal distribution, with vertical dashed or dotted lines indicating the corresponding probability values to different z-values. So we have two panels here. The top panel A shows one-tailed pz pairs, and the bottom panel B shows two-tailed pz pairs. For a one-tailed test, we have p equals 0.05 corresponds to z equals 1.64. P equals 0.01 corresponds to z equals 2.33. And p equals 0.001 corresponds to z equals 3.09. Then for the two-tailed tests, we have p equals 0.05 corresponds to z equals the absolute value of 1.96. P equals 0.01 corresponds to the absolute value of z equals 2.58, and p equals 0.001 corresponds to a z value of the absolute value of 3.29. Section 10.6.5, Misinterpretations. Below are 5 incorrect statements about a p-value of 0.02, which reflect misconceptions about the p-value. I would like you to explain why these statements are incorrect and then restate them so that they are correct. My answers and discussion are given below. Now, in the text, these statements are grouped together. First, all 5 incorrect statements, and then all 5 corrected statements, and then a discussion about all 5 statements. However, in this audio version, I'm going to read through each point, each statement, first with the incorrect statement, then correct it, and then provide a discussion about it. Statement 1. My p-value is 0.02, so the effect is present for 98% of the population. Here is a corrected version of that incorrect statement. My p-value is 0.02, so there is a 2% chance that there is no effect, and my test statistic was due to sampling variability, noise, small sample size, or systematic bias. Discussion. The p-value is about the average effect within the group in relation to the variability. It says nothing about whether the effect is present for each individual. Now, it is possible to determine whether an effect is significant within each individual, but that is not what the p-value indicates. Incorrect statement 2. My p-value is 0.02, so there is a 98% chance that my test statistic equals the population parameter. Corrected statement. My p-value is 0.02, so there is only a 2% chance that my test statistic was due to sampling variability or noise. I can follow up this result with a confidence interval analysis to determine the relationship between the observed sample mean and the unknown population mean. Discussion. The p-value says nothing about the relation between the sample and the population characteristics. It is simply the probability that the test statistic could have been observed if the null hypothesis were true. You can use confidence intervals to quantify the relationship between sample characteristics and population parameters. You will learn about that in Chapter 13. Incorrect statement 3. My p-value is smaller than the threshold, so therefore the effect is real. Corrected statement. My p-value is smaller than the threshold, so it is unlikely that the effect in the sample would have been observed given the null hypothesis, assuming that the sample is representative of the population. Discussion. A subthreshold p-value doesn't prove that the effect is real. It merely indicates that the observed effect is unlikely given the null hypothesis. Now, colloquially, we do refer to the effect as being quote-unquote real if the p-value is small, but that is not the most statistically appropriate interpretation. Incorrect statement 4. My p-value is smaller than the threshold, so therefore one variable causes the other. Corrected statement. My p-value is smaller than the threshold, so the variables are statistically significantly related to each other. Discussion. P-values do not, on their own, establish causality. Causal interactions can be determined through experimental manipulations or special kinds of analyses. A significant p-value does indicate a relationship between the variables, but other methods are required to determine causality. Incorrect statement 5. Imagine p equals 0.08 for this statement. My p-value is larger than the threshold, so therefore the null hypothesis is true. Corrected statement. My p-value is larger than the threshold, so the effect in the sample could have been observed if the null hypothesis were true. My specified alternative hypothesis is unlikely to be true, but there are other alternative hypotheses that could fit the data better than H0. Discussion. A supra-threshold p-value does not prove the null hypothesis. It merely says that the effect is likely to be observed under the assumption that the null hypothesis is true. There could be other models that explain the data better than H0 or HA. I hope you are not disappointed with these points. P-values are one tool in the statistician's toolbox. They are important, but they do not give all the answers. Section 10.6.6, Problems with P-values. I admit the title of this section is a little bit clickbaity. In fact, there are no problems with p-values. There are, however, some important limitations to relying exclusively on p-values to interpret statistical results. A few of these limitations have been described above. P-values do not prove an hypothesis, they do not prove causality, and they do not indicate the proportion of the population that exhibits effect. You will discover other limitations of p-values as you proceed through this book, including the fact that exceedingly small effects can be statistically significant if the sample sizes are large. The easiest p-values to interpret are really small, for example, less than 0.001, or really large, for example, greater than 0.3, because values near the extremes allow high confidence that an effect is really present or absent, and that repeating the experiment multiple times would lead to the same conclusion. P-values close to 0.05 are more difficult to interpret because it is possible that repeating the same experiment in a new sample, or even just adding a small amount of additional data, or changing the data cleaning pipeline, would change the p-value across the significance threshold, for example, from 0.054 to 0.046. On the other hand, the data are the data. You get the p-value that you get from those data, and it is unethical to manipulate the data or the analyses with the goal of obtaining a specific p-value. More discussion on this point in Chapter 18. Section 10.7, P-values and significance categorization. One of the challenging aspects of trying to understand the universe is that we cannot directly ascertain the mechanisms of nature. Instead, we collect data and assess whether an hypothesis about nature aligns with the data. In an abstract sense, our hypothesis is either true or false. However, we cannot definitively prove it with finite and imperfect data. Consequently, we rely on the p-value to make an informed decision about the validity of our hypothesis. As you now know, we label a test statistic as significant or non-significant based on the p-value. This categorization leads to a two-dimensional decision space, which is depicted in Figure 10.9. Figure 10.9 shows a table on the left and a Gaussian curve on the right. The table on the left shows the ways of making correct statistical decisions, and it is a 2x2 table. The rows correspond to the decision, don't reject H0 or reject H0, and the two columns refer to the reality about H0. H0 is true or H0 is false. The upper left cell corresponding to the decision, don't reject H0, and the reality that H0 is true is called a true negative, or 1 minus alpha. And the lower right cell, which corresponds to the decision of reject H0, and the reality is that H0 is false, this is called a true positive and is also called 1 minus beta. To the right of this table, we have a Gaussian distribution corresponding to a null hypothesis distribution of test statistic values. There is a vertical dashed gray line towards the right of the distribution, indicated as Z of alpha, and there's an arrow pointing to the left that says don't reject H0, an arrow pointing to the right that shows reject H0. The idea of the diagram to the right is to illustrate an analytical H0 distribution and the threshold for a test statistic value, Z of alpha, to be considered statistically significant. So any observed test statistic to the right of that threshold would be labeled as statistically significant. Back to the text. Figure 10.9, which I just described, shows that there are two ways of making correct decisions. You can reject H0 when it really is false, and you can fail to reject H0 when H0 really is true. There are also two ways of making statistical errors. I'll come back to these in the next section. But the problem with this entire approach is that we do not know the true state of the world and the reality about whether H naught is really true or false. Instead, we just have our empirical test statistic and our assumptions. Therefore, the decisions we make involve uncertainty. By the way, notice the wording of the decisions listed in that table. Don't reject H naught and reject H naught. You might think it would be better to write accept H naught and accept HA. Although stating that hypotheses are accepted based on a p-value might be permissible when speaking in hushed tones in dark, smoky basements, in formal statistical language, it is best to be precise. These statistical decisions are to reject the null or not to reject it. Section 10.8, Type 1 and Type 2 errors. Imagine these two scenarios. Scenario 1. Doctor says to a male patient, "You're pregnant." Scenario 2. Doctor says to a woman about to give birth, "You're not pregnant." These statements could be humorous enough for a late-night comedy sketch in the 1980s. How about these statements? Statement 1. Judge says to an innocent person, "You're guilty." Statement 2. Judge says to a murderer, "You're innocent." Not quite as funny, but both pairs of statements illustrate two kinds of errors that can be made when labeling a test statistic as significant or non-significant. Where do errors come from? Remember that we cannot prove that the alternative hypothesis is true, and that we reject the null hypothesis when the probability of observing a test statistic as large as our empirical test statistic is less than 5%. This means that it is possible to reject H naught when it is true, and it is possible to fail to reject H naught when HA is true. Footnote. Be mindful of the language here. We can imagine a world where the alternative hypothesis is true and consider the consequences. In empirical data, however, we can only compute the probability that the data are consistent with the null hypothesis. Back to the text. These are called Type 1 and Type 2 errors and can be added to the 2x2 decision space shown earlier. This paragraph references figure 10.10, which shows the full 2D space of statistical decision-making. So we have the same 2x2 table that I described from figure 10.9. As a brief reminder, the rows correspond to your decision, which is don't reject H naught or reject H naught, and the columns correspond to the reality about H naught, that H naught is true or H naught is false. I've already described the top left cell, which is called a true negative or 1 minus alpha, and I've described the bottom right cell, which is a true positive or 1 minus beta. Here in this figure, I'm also highlighting the upper right cell, which is called a false negative. That is when H naught is false, but the decision is don't reject H naught. This is also called a type 2 error. And the lower left cell is called a false positive or alpha or a type 1 error. This happens when H naught is true, but you reject the null hypothesis. Back to the text. Type 1 errors occur when you reject H naught when it is actually true. Type 1 errors are also called false positives or alpha errors. In other words, you conclude that there is a significant effect when there isn't one. The probability of making a type 1 error is the p-value significance threshold, and for this reason, type 1 errors are also called alpha errors. Type 2 errors occur when you fail to reject the null hypothesis when it is actually false. In other words, you conclude that there is no significant effect when there actually is one. The probability of making a type 2 error is related to the statistical power of the test, which is indicated by the Greek letter beta. Statistical power is defined as the probability of correctly rejecting H0 when it is false, thus 1 minus beta. You will learn more about statistical power in Chapter 17, but it is a quantity that you want to maximize, and it increases with larger samples, larger effect sizes, and lower variability. Type 2 errors are also called false negatives or beta errors. Consider the two pairs of scenarios I read at the beginning of this section. Which are type 1 and which are type 2? My answers are in the footnote, which I will now read. In both pairs, the first statement is a type 1 error because the verdict is true, pregnant or guilty, while the true state of the world is false, not pregnant or innocent. The second statement in each pair is a type 2 error because the verdict is false, not pregnant or innocent, while the true state of the world is true. Section 10.8.1, the balance of type 1 and type 2 errors. Needless to say, errors should be avoided in statistical significance and also in real life. Why not simply decrease alpha to, for example, p less than 0.0001? That would obviously minimize alpha errors compared to a threshold of p less than 0.05. Problem is that type 1 and type 2 errors have a push-pull relationship. Decreasing the probability of one increases the probability of the other. To understand why this is the case, let's travel to a fantasy world where we know with certainty that the alternative hypothesis is true, and where we have a huge amount of financial and lab resources to repeat our experiment many, many times. We would then have not just one test statistic, but an entire distribution of test statistics where HA is true. We can visualize the distributions under H0 and HA. This paragraph references figure 10.11, which shows theoretical distributions of test statistic values under H0 and HA. There are two Gaussians that are shifted from each other. The left Gaussian is called H0 distribution, and the right Gaussian is called HA distribution. There is a vertical dashed bar at somewhere around the top 5 percentile of the H0 distribution, which cuts the HA distribution at approximately half a standard deviation below the peak or below the mean of that distribution. Left of that distribution in the HA curve is shaded in dark gray and is labeled beta, and in light gray is shaded the area of the H0 distribution to the right of that vertical dashed line and is labeled alpha. So the dark gray shaded region indicates type 2 errors. So that is the alternative is true, but it was rejected. And the light gray shaded region indicates type 1 errors. So HA is false, but H0 was rejected. Back to the text. Please take a moment to meditate on figure 10.11 and make sure you understand how the chosen alpha threshold determines the probability of making false positives or false negatives. Also, keep in mind that in practice, you have only one test statistic for HA. The distribution of HA is conceptual and illustrates that even if your hypothesis is true, repeated samples may provide different test statistic values, some of which could be below your alpha significance threshold and would therefore be incorrectly labeled as non-significant. Back to the push-pull relationship between these two types of errors. The more stringent the p-value threshold for rejecting the null hypothesis, that is, the further to the right you push the vertical dashed line in the figure I just described, the less likely you are to make type 1 errors, which is good. But the more likely you are to make type 2 errors, which is bad. This means that even if your hypothesis is true, you may fail to reject the null hypothesis. This paragraph refers to figure 10.12a. To be honest, figure 10.12 is difficult to describe accurately purely in words. I'd strongly recommend having a look at the text figure or reproducing it yourself with the Python code. I will try to describe the main take-home messages from each panel. So panel A shows two Gaussian distributions, one on the left corresponding to the null hypothesis distribution and on the right corresponding to the alternative hypothesis distribution. In this case, the vertical dashed line indicating our statistical significance threshold is roughly aligned with the peak of the HA distribution. This means that the alpha range for type 1 errors is very small, but the beta range for type 2 errors is very large. Back to the text. Next, let's pull the critical value to the left in panel 1012b. Now you are less likely to make type 2 errors, but more likely to make type 1 errors. This paragraph references figure 10.12b, which shows the same two Gaussians that I just described for panel A, except now the vertical dashed line corresponding to the significance threshold is at the valley between the two distributions, and the range of alpha, or the area covered by alpha and the area covered by beta, is roughly equal. But the idea is that the alpha area, or the type 1 error probability, is much bigger than it was in panel A, although the area for the type 2 errors, or beta, is much smaller than it was in panel A. Back to the text. Of course, an optimal scenario involves pushing the distributions away from each other to minimize the possibility of any statistical errors. This is shown in panel C. You can make this ideal situation more likely by increasing the effect size or decreasing the variability. I'll talk more about why that is in the next chapter on t-tests. This paragraph refers to panel C, where we see a similar setup as in panel B, except that the two distributions are further apart, so the total overlap between them is very, very small. The area for the alpha errors and the area for the beta errors are roughly equivalent, but they are both much smaller compared to the areas for the statistical errors depicted in panels A and B. Back to the text. But the reality is that you don't know the true state of the world, which means you don't know the distribution of HA values. Instead, you have only one HA value, and you are left wondering whether that one empirical test statistic value is a relatively unusual value drawn from the null distribution or whether it is a value drawn from the alternative distribution. This paragraph references panel D, which shows only one Gaussian corresponding to a theoretical or an analytical null hypothesis distribution, and an arrow pointing down towards the right of the distribution indicated as observation. This is your observed data. The idea is that in reality, you get just one observed test statistic value and must decide whether it belongs to the H0 distribution or to the HA distribution. Section 10.9, Various Interpretations of Significant. If the p-value of the test statistic is small enough, then we say that the effect is statistically significant. But that is not the only interpretation of the word significant. Findings can be significant statistically, theoretically, clinically, socially, or practically. There are many ways to interpret the significance of a finding. Statistical significance. This is the primary use of significance in statistics books and research reports, the probability that an empirical test statistic would be observed if the null hypothesis is true. Theoretical significance. In this context, theoretical refers to a scientific theory, not an abstract concept or analytical formula. Theoretical significance means that a finding is relevant for a theory or leads to new experiments. This type of significance has nothing to do with statistical significance. A finding can be highly theoretically relevant, yet not statistically significant. Clinical significance. This means that a finding is relevant for diagnosing or treating a disease. As with theoretical significance, this is unrelated to statistical significance. For example, finding that a vaccine has no statistically significant relation to autism has high clinical significance while being statistically non-significant. Practical, societal, educational, etc. You can see where this is going. The outcome of scientific research can have many possible implications or significances. These various real-world implications may be informed by the p-value, but a finding does not automatically have, say, educational significance, simply because the p-value is less than 0.05. This list highlights that statistics lives at the boundary between the hard sciences, mathematics, and the softer sides of things, implications for policy and decision-making. The mathematical geniuses of statistics gave us p-values, and computers compute those p-values to a high degree of numerical accuracy. But it is up to you, the researcher, to use those p-values appropriately to make decisions about what the data mean and don't mean, how to interpret them, and how to use those data to expand the boundaries of human knowledge and improve society. All that said, when you encounter the word significance in any statistical discussion, you can assume that this term refers to statistical significance, and in particular, whether a p-value is above or below 0.05. Any other implications of the word significance are generally accompanied by a qualifier like clinical significance or practical significance. You can see from this section that the terms significant and non-significant bring with them a number of connotations and implications. An alternative categorization of p-values is subthreshold, p less than 0.05, or suprathreshold, p greater than 0.05. These terms are particularly useful when many tests are performed, for example, during multiple comparisons corrections. Section 10.10, Multiple Comparisons. The term multiple comparisons refers to the practice of testing multiple hypotheses within the same dataset. While it is advantageous to extract as much information as possible from a dataset, particularly when the experiment was costly or time-consuming, conducting multiple hypothesis tests within the same dataset can pose statistical challenges. Specifically, with each additional test, the risk of false alarms or type 1 errors increases. This is known as the multiple comparisons problem. Fortunately, there are statistical corrections that can minimize the likelihood of erroneously rejecting the null hypothesis. When performing multiple comparisons, don't think about the individual tests. Think about the set of hypotheses being tested. This is called a family of tests. The more members in the family, the more likely it is that at least one finding is incorrectly labeled significant. In other words, with increasing family size comes increasing risk of type 1 errors. Why does this happen? Remember that the p-value is the probability of finding a test statistic of a certain size, assuming that the null hypothesis is true. The more samples you draw from the H0 distribution, the greater the chance of drawing a random sample from the tails of the distribution. Now, let's imagine an experiment with 3 conditions, and we want to compare each condition against each other condition. This is visually depicted in figure 10.13. 10.13 shows a depiction of multiple statistical tests in 3 samples, where each test is evaluated at p less than 0.05. The figure shows 3 circles. The left circle is filled with squares, small squares. The middle circle is filled with small triangles, and the right circle is filled with pentagons. These are just abstract visualizations of 3 different samples. Underneath that, we have 3 rows of text showing hypothesis 1 is squares versus triangles, hypothesis 2 is pentagons versus triangles, and hypothesis 3 is squares versus pentagons. The idea that this figure is depicting is that we have 3 samples, maybe this is 3 different samples or 3 different conditions from the same participants, and we can generate 3 different hypotheses of pairwise comparisons. Back to the text. Assuming we test each comparison using a threshold of p less than 0.05, then our 3 tests give a combined probability of making a type 1 error of 0.15 or 15%. That's quite high. It means that we have a 15% chance of incorrectly labeling at least one comparison as quote-unquote significant when none of the conditions actually differs from each other. Now, to be clear, each individual test is evaluated at p less than 0.05, but the family of tests has a total false alarm rate of 0.15. The error rate of the family of tests is called the family-wise error rate, often abbreviated FWE. Where does 0.15 come from? I'm sure you figured out that 0.15 is 3 times 0.05. In other words, the family-wise error rate is computed as n times alpha, where n is the number of tests, and alpha is the significance threshold, typically 0.05. Actually, setting FWE equals n alpha is not necessarily accurate. Dependencies in the data and between the tests can decrease the family-wise error rate. A slightly less conservative estimate is computed as 1 minus the quantity 1 minus alpha to the power of n. Still, the dependencies in the data and among the tests can be difficult to know or estimate. An example of dependencies in the tests is if we compare conditions A versus B and A versus C. In this case, the tests are correlated because they both involve A. It could also be that data in conditions B and C are related to each other. Section 10.10.1 Solutions to the Multiple Comparisons Problem. Solving the multiple comparisons problem involves adjusting the p-value significance threshold so that it matches the family-wise error rate instead of the individual test threshold. There are several correction methods you can apply depending on the nature of the data and the number of tests. Below is a description of a few popular options without implying that any method not in this list is inappropriate or invalid. You will learn more correction methods in Chapter 14 on ANOVAs. First, we have Bonferroni. Bonferroni correction is a simple and commonly used method. It involves setting the family-wise error rate to be the desired threshold, for example, 0.05, and then the individual test thresholds as alpha divided by n, where n is the number of tests. In the example depicted in figure 1013, this is the figure with the 3 abstracted data sets that I described a few moments ago. Each of the 3 tests would be evaluated using a threshold of p less than 0.05 divided by 3, which means each individual test is evaluated at p less than 0.01667. Bonferroni correction has 3 limitations. First, it can be too stringent because it assumes independence among the tests. 2, it is based solely on the number of tests and not on the characteristics of the data, which is problematic for correlated data such as time series and images. And 3, it increases the probability of type 2 errors and therefore can prevent true findings from being identified. Therefore, Bonferroni correction is appropriate when the number of tests is not so high, let's say in the single digits, although there's no specific cutoff, and when the tests are independent of each other. Another correction method is false discovery rate, often abbreviated FDR. FDR correction is useful when you have many p-values from correlated tests, such as time series, images, geographical data, or genomic data. FDR is an algorithm that produces a corrected threshold called Q that is computed from the distribution of p-values. Q is defined as the ratio of the expected number of false discoveries to the expected number of true discoveries. I'll explain the algorithm in more detail in exercise 4. The limitation of FDR is that the threshold depends on the set of p-values evaluated. This means that a particular finding might be labeled as significant or non-significant depending on the other p-values. Another method is cluster correction. This is appropriate for data that have a correlation structure, such as time series or images. The idea is to consider a test to be significant only if it is within a set of contiguously significant tests. This paragraph refers to figure 10.14, which shows a block matrix with a bunch of different grayscale colors, and there are some clusters of cells in this matrix that are white and connected with a dashed line. There is another isolated white box or cell that has the letters NS in them, which stands for non-significant. The caption reads, "Imagine statistical tests on a geographical grid where the grayscale intensity corresponds to p-value and the white squares indicate p less than 0.05. Cluster correction would label a non-contiguous white square as non-significant." Back to the text. The minimum cluster threshold can be determined based on a priori considerations. For example, a cluster must contain at least 100 milliseconds of contiguously significant time points, or at least 6 spatially contiguous significant pixels, or based on permutation testing to derive an empirical cluster size under the null hypothesis. Do you always need to correct for multiple comparisons? Methods to correct for multiple comparisons are designed to control for type 1 errors, but have the side effect of increasing the probability of type 2 errors. Therefore, multiple comparisons corrections should be used when possible, but they should also be interpreted appropriately. In particular, understanding that true effects are more likely to be labeled as non-significant when the FWE rate is controlled. What about findings that are item-wise significant at p less than 0.05, but do not survive correction for multiple comparisons? You can consider 3 categories for findings: non-significant, so p greater than 0.05, significant without correcting for multiple comparisons, and significant when correcting for multiple comparisons. This quote-unquote intermediate category may be relevant for theoretical significance of the study, but it should be interpreted cautiously and qualitatively. Section 10.11, Degrees of Freedom. Here's a question. If I tell you that the mean of a 3-element data set is 5, and that 2 of the numbers in that data set are 2 and 3, can you tell me the third number? Yes, you could. You know that 5 equals the quantity 2 plus 3 plus x divided by 3. And so the third number must equal 10. In other words, I told you n-1 data values and a sample statistic, and you could calculate the nth data value. This example illustrates a system with 2 degrees of freedom. So given 3 numbers and a known average, there are only 2 numbers that are free to vary. The third value cannot vary because its value is determined by the other 2 and by the average. Margin note: degrees of freedom are often abbreviated to DF, typically in italics. Back to the text. Here is a more formal explanation. A descriptive statistic is computed from data, and it might additionally have constraints. The degrees of freedom is the number of independent pieces of information that can be varied without changing the constraints. In the above example, the 2 data values, 2 and 3, are independent pieces of information, and the average value provides the constraint. Degrees of freedom are used as parameters of H0 distributions, which means that DF are used to make inferences about the underlying population. You can also use the DF to check for errors and correct interpretations of results in regressions and ANOVAs. There's no single formula to compute the DF in all analyses. As a general rubric, you can think of the DF, degrees of freedom, of an analysis as the number of observations minus the number of parameters. That is, DF equals n minus k. Now, depending on the analysis, n might be the number of individuals in the study, or it might be the number of groups or conditions in the experiment. Furthermore, certain analyses involve corrections to the degrees of freedom to account for violations of analysis assumptions. Therefore, I recommend memorizing the expression degrees of freedom is the number of observations minus the number of parameters, but also remember that that is a useful simplification, not a ubiquitous mathematical law. A few examples. The DF associated with a t-test is either n-1 or n-2, depending on whether there is one group or two. The DF associated with a correlation is n-2 because there are two variables. The DF associated with a regression is n-k, where k is the number of independent variables. Now, don't worry about memorizing those formulas. They'll make sense in later chapters. Degrees of freedom are usually integers, but do not need to be. Some analyses apply correction factors to the degrees of freedom, for example, to compensate for differences in variance. Section 10.11 is the exercises. I encourage you to check out my YouTube channel for explanations of the problem sets and the solutions in Python. End of chapter 10.